you'll be able to receive signal from at some time. And it's defined to be this integral. And in the case that we're looking at, that integral is finite. So there's a cutoff point where after that cutoff point, chi values larger than that, you won't receive signal from them. Those points, even at, you'd have to wait an infinite amount of time. So it's a physically meaningful distance. Okay, so now a sequence of lemmas that allow me to prove the result I've been referring to. And some of them I'm proud of, others are pretty straightforward. So this one just says that at a fixed Robertson-Walker time, you have this inequality, which has to do with what I just said in terms of chi values being less than this cutoff point. To show that it is true, you do a substitution and you integrate by parts. I was reading about how to do a math presentation. They said don't prove every little thing you do. So there's nothing too fancy here. So I think I'll move on. Another lemma that is needed, these all come together in an awesome way though, is that again, if as your time goes to infinity, the largest chi values at the fixed Robertson-Walker time approach the cosmological event horizon. This time we use L'Hopital and Leibniz rule, so again, I couldn't stop myself from showing this proof because that shows up a lot, especially Leibniz rule, which I will, if you don't remember it, maybe you didn't see it in analysis, I'll put it up in a few more slides, but it's a useful trick that gets used a lot, or at least by me. And here's one I'm going to go through. I'm going to go through this proof in detail. So this says that the chi function is increasing as a function of tau. So this is useful, a useful result, and it's a fun proof. So I'm going to go through it.
Wait, I'm sorry. It's increasing and yet it has a finite limit.
Yeah. So it one of those. Like it's going up, but it.
Second. Okay. So comment on the second derivative.
Okay. Asymptotic.
Sure.
Yeah. Okay. So chi. I'm going to write it as f over g. It was 1 over this times this integral. So just think of that as two separate functions. And again, this is all because this is not a max integral, if you can imagine. So by the quotient rule, this derivative is positive if and only if this condition is satisfied. So now we can look at the derivatives of f and g and their ratio, and that's useful because the derivative ideally will let me get rid of the integral in f, and then things aren't so bad. So again, Leibniz rule, arguably I could have put it on an earlier slide, but I will remind you of what it is if you don't remember it. The quotient on the right. So if you actually take that derivative, you do indeed get rid of that integral. Looks like this. Now, the last term on the right, you can convince yourself that it's always greater than 1, because Ts is greater than 0. And so then that gives that the ratio of the derivatives of f and g is always bigger than this, which is chi horizon. And we showed that chi s is less than chi horizon, so now you have that chi s, which is f over g, is less than chi horizon, so the inequality we wanted holds. If I didn't explain that well, let me know. But that was, I'm stoked on that. It was fun. We're trying all these ways to prove it, and quotient rule. Okay. So I told you I would remind you what Leibniz rule was. It is this. It lets you bring the derivative inside the integral, which you can often do, except here you've got variable where the limits of integration depend on the variable you're taking the derivative with respect to. So you can't just bring the derivative inside, you pick up some extra terms. Now, in a sec, there's going to be an issue because this lower limit, you have to plug it in here. But if f is undefined at that lower limit, that's bad, then you get infinity. But if the lower limit's a constant, well then this is 0 times infinity. Who wins in that scenario? Do you get a finite number, do you get 0, is it still infinite? So in the case we're worried about...
Excuse me,
yeah.
Can you go back,
yes.
please?
Is there a typo?
What did you say about ut constant?
Oh, so in the case I'm going to worry about, this lower limit of integration will be a constant.
If it's constant, what happened?
Well, in general, you would just get 0 here because of this.
This will not be applied. You stop at the first line, right?
Well, but the constant f is undefined there. So there is a, it's infinite.
You don't write it, the second term. If it's 0 and there is a problem, you are dealing with the improper integral, but
right.
The formula is not valid.
Right, exactly. So I'm going to show that in a specific case, it does follow what Leibniz rule would say, and this term just loses out. But you can't just always say that, but in a specific scenario, I'm going to show that you can. Is that, or, yeah. So I'll show you exactly what I mean. So here's the f I'm going to use, here's the u, here's the v, here's the where tau can be, and so this and this equality ends up being the case. This is, again, another lemma that is needed for what we're getting at. And it is an issue, so that's why it gets its own lemma. So the first thing I do to the integral is break it up, pick a d in between these so you can break it up. Here, Leibniz rule, you can just apply to that first one because nothing's bad about it. But then, so the second term though, we need to show that this holds, because then the 1 to d in this integral will combine with the d to sigma in the other one, and it'll give the equality that I stated in the beginning. Just to not have to write all the stuff in the integrand, I'm going to write it like this. Okay, so we need to show that this is true. We need to be able to bring that derivative inside. Okay, so the left-hand side, sorry, you're not supposed to go back and forth. The left-hand, this derivative exists provided that for all non-zero sequences tau n, whose limit goes to 0, this limit exists. And the derivative does exist because it's a coordinate function. So, but you can show that quickly from contradiction. So, so this, we can switch this continuous limit to a sequential limit. And that'll hold for any non-zero sequence tau n. So pick one of those non-zero sequences that go to 0. Now, to show what I'm trying to show, use the dominated convergence theorem, but to do that you need a bound on the integrand. To get that bound, apply the mean value theorem for derivatives. So I was trying to find a bound on this, which is messy. The mean value theorem for derivatives says that it will equal the partial derivative of f with respect to tau at some point sigma comma tau hat, where tau hat's in this interval. So what this lets me do is just find a bound on the partial derivative of f, which is good because it's neater than that, and I know what it is. The partial derivative of f, in the case we're talking about, just to mention, a is the a that I've been talking about the whole time. A of t is t to the alpha. B is its inverse, and the dots represent differentiation. So just plugging what t to the alpha and t to the 1 over alpha in and whatnot, and the various derivatives, you get that the partial derivative of f with respect to tau is this. I mentioned that tau is on this interval. Tau is in the lowest it gets is Ts, and it goes up to infinity. So, as a function of tau, that guy is decreasing, so it has a maximum value of just plugging in this lowest value. Now we just have a function of sigma, call it g of sigma, and this is true. I didn't write the closed form of g on here because it's very messy. It's a bunch of like hypergeometric functions and whatnot, but it is true that it is integrable. And so we can use the dominated convergence theorem and bring this limit inside, which lets us do this, which lets us do what we wanted. So yeah, it's not obvious. I couldn't just say what I wanted to say. So.
Well, the way I see it is the following. Leibniz rule, you need a regularity on your function and on the u and the v. It happens in your case that your function has a singularity. It's singular at 1.
Mm-hmm.
So what you do, you remove this singularity. You go from 1 to d, and from d to your v. It's a nice function. You apply Leibniz rule.
Yeah.
And at the singularity, you treat it directly.
Yeah.
You go after it.
Exactly, yeah.
It's what you are doing.
Yeah, exactly. So yeah, that was fun. My roommates here saw me happily work on that problem for a while. So here's a physically meaningful set. It's defined just to have positive time values. So every time after the Big Bang and every chi value, all chi values at a given time that are within the cosmological event horizon. So this is the set of all eventually observable events. If you don't have an inflationary cosmology, this set represents all space-time points. Fantastic. Other than the Big Bang itself. This is open there, so you don't get to see that. Okay. The last lemma is really technical, and want to get to a few other things and questions. So, but what it does is it says that you have a coordinate transformation from tau sigma, which are I think of as almost Fermi coordinates, to the t chi coordinates. That you have a diffeomorphism, and it uses all the lemmas we established before to get that. And so, where is this transformation valid? It's going to be on the set of analogous set of positive Fermi time values and rho values that are within the radius of the Fermi space slice. And so, as I mentioned, you can convert from sigma to rho. And here's the thing I said that it was easy to get from tau sigma to tau rho coordinates. You define these guys, and they're all smooth functions, so then you have this diffeomorphism with an inverse, and then you define this, and that's your transformation to tau rho coordinates. And so it goes from the set of all observable events, that V, to that physically meaningful set of all positive time values, where the distance is within the radius of the Fermi space slice. Okay, so the theorem that we were after, that all those lemmas put together, more or less there was one other thing in there, which is that the Jacobian determinant of the coordinate transformation we were looking at is positive, provided that d chi d tau is positive. And we showed d chi d tau is positive. So that was really the only other step in this. So here we get what I was saying, which is that you have Fermi coordinates and the transformation's valid in V. So Fermi coordinates extend to the cosmological event horizon. It's a really cool result that says you have a coordinate transformation that's valid, not everywhere, but everywhere that you could possibly care about because it's everywhere you could ever observe. Okay, and then direct, this guy doesn't fit in the box exactly, but direct computation shows that the metric in these coordinates is as follows. This is nice, there's no coefficient there, but the coefficient or the time coordinate is messy. In 2 dimensions, you can ignore the stuff after the second addition sign. Okay, so, all right, 2 examples that I would like to get to, so there's some physical interpretations happening. The Milne universe is a prototype universe with no matter or energy.